Hello everyone, welcome to my channel. Now in this video I am going to discuss the topic thermal expansion under the chapter thermal properties of matter. Now suppose we have a body, okay, in a material. Now to this material heat is given. Now there may be an expansion in this body. There may be a rise in temperature in the body, or there may be a change in state. This body may melt, or this may, if suppose this is liquid, this may be converted into its vapor phase. Okay, so these are the various things, various possibilities when heat is given to a substance or a material or a body. Okay, now in this first part we are going to study about thermal expansion. Now basically, see, when we are giving heat to a body, then the molecules of this body, they are acquiring heat, they are acquiring energy. Now heat is a form of energy. So now if these are two molecules, okay, now suppose they are vibrating like this. Okay, now in case they are supplied with this excess heat, the separation between the molecules, it increases because of the increase in energy. Now since the separation increases, the size of the overall material, it increases and the material undergoes expansion. So this is the fundamental idea about expansion. Now there are certain materials which contracts on heating. There are certain exceptions, like if you heat rubber, okay, now this will contract on heating, but otherwise all the materials, they undergo expansion when heat is supplied to them. Okay, now this expansion, thermal expansion, it is of three types. Thermal expansion, it is of three types. Okay, three types: linear expansion, aerial expansion, aerial or superficial expansion, and volume expansion. Okay, now in which case the expansion will be called as linear expansion, in which case it will be called as aerial expansion or volume expansion, let us analyze it now. Now suppose you have a scale or a rod of length 10 centimeter. Okay, you have a rod of length 10 centimeter. Now of same material you have another rod of length, say this is 100 centimeter. Okay, now both the rods are of same material. Okay, one rod of 10 centimeter length, the another rod of 100 centimeter length. Okay, now this length is quite large as compared to the other dimensions. Okay, now suppose this heat is given to both the rods. Now both the rods are supplied with, say, 1000 calorie of heat. Okay, this is also supplied with 1000 calorie of heat. Okay, now let's assume that length of this rod increases to 110 centimeter. Okay, so this 100 centimeter becomes 110 centimeter. So if 100 becomes 110, this 10 becomes 11, isn't it? If 100 is becoming 110, there is a 10% increase in length. For this 10 centimeter length rod, the final length will be 11 centimeter. So that means, see, for this 100 centimeter length rod, the increase in length is 10 centimeter. Okay, the increase in length here is 10 centimeter, but for this it is 1 centimeter. Okay, so that gives an idea that if initial length is more, the increase in length is also greater, higher. If the initial dimension is small, the increase in dimension is also small. Okay, so that means, see, if you have a material like a rod, okay, now for this rod, obviously this length will be quite large as compared to this other dimension like thickness, radius and all. So that means if heat is given, the extent of expansion in terms of length will be far greater as compared to other dimensions like increase in radius. So like if you have objects of this shape like rod, then we have to consider their linear expansion. Okay, now suppose you have a metallic sheet. Okay, this is a metallic sheet. Now for this, suppose this is the length and this is the breadth. Okay, now in this case there are two dimensions which are quite pronounced, but the third dimension, that is the thickness, it is quite negligible. So when the heat is given, the increase in thickness will be quite negligible, but the increase in length and increase in breadth will be observable. So in this we need to consider the increase in area. Okay, so for this kind of things we will study areal expansion, areal or superficial expansion. Areal expansion is also called superficial expansion. Okay, now if you have an object of, say, of cubical shape. Okay, now in this case, see this breadth. So this is the breadth, this is the length, and this is the height. So all the three dimensions in this case are pronounced. Okay, so when heat is given to this, there will be increase in breadth, increase in length, and increase in height. So for such objects where all the three dimensions are more pronounced, for that we will be considering, when heat is given, we will be considering the volume expansion. Volume expansion. Okay, so this is the fundamental thing where we have to consider about linear expansion, where we have to consider areal expansion, where we have to consider volume expansion. Okay, now another, so now this where we'll be using which expansion, that concept is clear. Now first let us study linear expansion. Now as we have seen here, see when this heat is given, same amount of heat is given to both the rods of same material, the increase in length in the rod, this rod is more because its initial length was more. Okay, so from this we conclude, so for linear expansion, the first observation is if you have a rod of length L0 at temperature T0, okay, and this length becomes LT at temperature T. Okay, so the increase in length, it is LT minus L0, it is proportional to L0. Okay, if initial length is more, the increase in length will be more, as we have seen in the previous example for rod of length 100 centimeter and 10 centimeter. Okay, now obviously this LT, this is proportionality symbol. Okay, so LT minus L0, the increase in length, obviously it will be proportional to the increase in temperature. Greater the increase in temperature, greater will be the increase in length. Now if I combine these two conditions, what do I get? I get LT minus L0 proportional to L0 T minus T0. Okay, now if I remove this proportionality symbol, I get a constant LT minus L0 is equal to alpha L0 T minus T0. Okay, this alpha is the proportionality constant. See, this is not alpha, this is proportionality constant, but this is alpha. Okay, now this is proportionality constant, it is called coefficient of linear expansion. Coefficient of linear expansion. Okay, now this value is a constant, its value will depend on the nature of the material, nature of material of this rod. Okay, it is independent of temperature and other factors. Okay, so this is alpha. Now from this I can write alpha is equal to LT minus L0 divided by L0 T minus T0, or I can write this in differential form also, like alpha is equal to LT minus L0 is the change in length, so dl by L T minus T0 is dt. So what will be the unit for this coefficient of linear expansion? This is in length, this is also length, so this unit cancels out, so we are left with this temperature. So unit of alpha will be per degree Celsius or per Kelvin. Okay, now next is superficial or aerial expansion. Aerial expansion. Okay, now as the length, increase in length is proportional to the original length, increase in length is also proportional to the rise in temperature. Similarly, if you have a sheet, okay, now this is area S0 at temperature T0, now this area becomes ST at temperature T. Okay, T is greater than T0, so increase in area ST minus S0, it is proportional to the original area. Okay, this ST minus S0 is also proportional to T minus T0, that is a rise in temperature. So if I combine these two conditions, what do I get? I get ST minus S0 proportional to S naught T minus T naught. Okay. So if I remove this proportionality constant, I get St minus S naught is equal to beta S naught T minus T naught. Now this beta is the proportionality constant, and it is called coefficient of areal expansion, coefficient of areal or superficial expansion, superficial expansion. Okay, so beta is St minus S naught divided by S naught T minus T naught. So coefficient of superficial expansion is defined as increase in area, this is increase in area, per unit area, this is the original area, per unit rise in temperature. Okay, and how about the unit? This area cancels out, so the unit of beta is per degree Celsius or per Kelvin. Okay, now similarly for volume expansion, this suppose V naught is the volume at temperature T naught and Vt is the volume at temperature T. T is greater than T naught. So when the temperature increases from T naught to T, volume increases from V naught to V. So we have Vt minus V naught is equal to gamma V naught T minus T naught, as in the previous two cases. Now here the proportionality constant is called gamma. So Vt minus V naught is proportional to V naught. Vt minus V naught is also proportional to T minus T naught. That is, the increase in volume is proportional to the original volume. Increase in volume is also proportional to the rise in temperature. Gamma is the proportionality constant, and it is called coefficient of cubical expansion. Coefficient of cubical expansion. So we have gamma is equal to Vt minus V naught T minus T naught. So gamma is increase in volume per unit rise in temperature. So unit of gamma is also per Kelvin or per degree Celsius. Now in this calculus form, this can be written as dV by V, and this is dt. Now this thing can also be written in calculus form as ds by s dt. St minus S naught is ds, change in area, change in temperature is dt. This is the original surface area. Okay, so this is the basic concept of the linear expansion, area expansion, and volume expansion. Let us see the relation between the three coefficients of expansion, that is relation between alpha, beta, and gamma. See, the variation in length with temperature, that is, we have obtained previously that Lt minus L naught is equal to L naught alpha T minus T naught. Now let us say I replace this T minus T naught as delta T, that is a change in temperature. Then this becomes L naught alpha delta T. If I take this L naught to the other side, we have Lt is equal to L naught 1 plus alpha delta T. Okay, where alpha is the coefficient of linear expansion. Now similar to this, for I can write St, the surface area at temperature T, is equal to S naught 1 plus beta delta T, and for volume Vt is equal to V naught 1 plus gamma delta T. So we have to find a relation between this alpha, beta, and gamma. Okay, so we have this relation. Now let us square the equation both sides. So squaring both sides, so this is Lt square is equal to L naught square 1 plus alpha square delta T square plus 2 alpha delta T. Now see, this alpha value for the materials is very small. It is of the order of 10 power minus 5, 10 power minus 4. Delta T is also small. Now alpha square and delta T square will be further very small. So that means this term can be neglected. Now if we neglect this term, we have Lt square is equal to L naught square 1 plus 2 alpha delta T. Okay. Now square of the length is area, which is like area. So this is St is equal to S naught 1 plus 2 alpha delta T. Okay, but we have already seen that St is equal to S naught 1 plus beta delta T. So if I compare the coefficients, instead of 2 alpha I am getting beta, so that means beta is equal to 2 alpha. So that is the relation between alpha and beta. Okay, now similarly if I take cube on both sides, okay, so cubing both sides, cubing both sides, what I get, LT cube is equal to L naught cube. This is a plus b whole cube. So that's a cube plus b cube plus 3a square b plus 3ab square. So this is 1 plus alpha cube delta t cube plus 3 alpha delta t plus 3 alpha square delta t square. Okay, so again this term, alpha delta t both are small, so higher powers of alpha and delta t can be neglected. Okay, these terms are neglected, so we are left with LT cube is equal to L naught cube 1 plus 3 alpha delta t. Okay, now length cube is equivalent to volume, so this is Vt is equal to V naught 1 plus gamma delta t. Okay, so now again if we compare the coefficients, what do I get? Gamma is equal to 3 alpha. So from this we have the relation between alpha, beta and gamma as alpha is equal to beta by 2, alpha is equal to beta by 2, and here alpha is equal to gamma by 3. So that is equal to gamma by 3. So this is the relation between alpha, beta and gamma. So hope things are clear to you and you find this video useful. And in case you have any difficulties in understanding further concepts or things related to this video, you can post in the comment box. And if you have really liked this video, do subscribe to my channel, and you can also share this video with your other friends. So good luck.